Welcome to Mark's Tech Talk. In this video, we're going to introduce op-amps. Op-amps is short for operational amplifier. And operational amplifiers can be constructed with discrete transistors or even vacuum tubes. Most often today, they are an integrated circuit. And an ideal op-amp, ideal operational amplifier, has infinite gain, infinite bandwidth, infinite input impedance, and zero output impedance. Well, of course, that's the ideal. In the real world, the gain is not quite infinite, and nor is the input impedance, and output impedance isn't quite zero. More typical values that you'll see for gain is somewhere in the area of 10,000 to 100,000, which is still exceedingly high gain, very, very high gain. Same thing with input impedance. It's not infinite, but 1 mega ohm could be a typical value. Very high input impedance. Output impedance generally in the range between 50 and 200 ohms. Again, all these parameters are going to vary a little bit with a specific device and the manufacturer, but this will give you some ballpark numbers. Now, once you actually hook these up in a circuit, that's going to change things. It's going to change your effective input impedance and your gain and so forth. So let's look at how these are commonly used. There's a lot of different configurations for op-amps. We're going to look at the most common. First of all, when you have an op-amp, we'll designate that with a little triangle. That's kind of the generic symbol for an amplifier. And an op-amp typically has two inputs labeled with a plus and a minus. The one labeled with a plus is called the non-inverting input, and the minus is the inverting input. And that refers to the phase of the signal between the output and the input. So if the first half of your waveform is positive and you apply it to the non-inverting input, then the first half of your output waveform will be positive. On the other hand, if you apply the positive first half cycle waveform to the inverting input, then the output first half cycle will be negative. In other words, it flips it around. The inverting input flips it around, the non-inverting keeps it in the same phase. Additionally, op-amps will use a dual power supply, so you have to have both a plus and a minus voltage in order to operate the op-amp typically. So that's just kind of generic across all op-amps. Here is a specific configuration. This is called an inverting configuration because we're using the negative or inverting input of the op-amp. So we have a resistor in series, and we have a resistor feeding back from the output back to the input. That is the feedback resistor. The Rn is the input resistor. If we take the ratio between those two, Rf divided by Rn, that will give us the gain of this configuration, the gain of the amplifier, and gain is simply the voltage out divided by the voltage in. But we also have to notice that because we're using the inverting input, our gain is really a negative number. In other words, it's going to invert the phase. It's going to flip the waveform. So our gain is given by A. In this case, it's going to be a negative gain because we're using a negative input, the inverting input, and it's given by RF divided by Rin. If we use the non-inverting input, slightly different configuration. Here the input resistor is down on the negative and the feedback is on the negative. The feedback, we always use a negative feedback, so that's always going to go back to the negative terminal. Your gain now is 1 plus RF over Rin. So slightly different. Notice we don't have a negative here. We're using non-inverting input. Slightly different formula for our gain, and there is no negative on it. Here is a differential configuration. Here we're using both inputs together, and essentially what it does is subtract those two inputs. So we have V2 minus V1 multiplied by the gain gives you the output voltage. So the difference between the input voltages multiplied by the gain gives you the output voltage. And this is the configuration. Notice again, feedback resistor is going to the negative terminal. Okay, so This is a differential configuration of an op-amp. Okay. Notice on all three of these configurations, and generally speaking with an op-amp, we don't have capacitors here because we want to pass the DC. That's a kind of another neat feature of op-amps is they actually amplify DC. So if you don't want to do that, you can add a coupling capacitor, but many times you actually want to amplify the DC. For example, if you're using an instrumentation amplifier, so you may have a small DC signal that represents perhaps a temperature or pressure or something like that, and you want to amplify that before you put it into an analog to digital converter or something like that. So you can use an op-amp and just amplify the DC. All right, this is another configuration. This is called the summing configuration. This is where we have multiple inputs and we add them together. So each voltage is multiplied by the gain, and then this is fed into the inverting input, so everything is going to get flipped around. We put a minus sign in front. So V out is equal to minus the quantity RF over R1 times V1 plus RF over R2 divided by multiplied by V2 and so forth. Okay, so you sum up voltages and then amplify it, summing configuration. So these are the common configurations that you're most likely to run into. There are many, many more configurations to do different things, but this will give you just a bit of an intro into op-amps or operational amplifiers. Hope you enjoyed this edition of Mark's Tech Talk. Stay tuned for more.